So this is a short discussion of the material in section 4.4, which kind of takes everything that we've learned up to now, how to find asymptotes, and some that we learned in previous courses, like how to find intercepts, um, but also about how to use, find critical points, where the derivative is zero, where the derivative is not defined, how we can use the derivative to determine where a graph is increasing or decreasing, or use the second derivative to know where a curve is concave up or concave down, and also to find points of inflection. So I have to tell you, so this is really, I think this is how people used to graph, and we're gonna use all this information to create a graph. And I think this is how people would graph before calculators and computers. So I don't know that anyone really does this now. But you're not actually going to have a quiz on this, or it will be on your third exam. But what I'm going to do is I'm going to give you the problem ahead of time, and then so you can prepare it. So when you submit your quiz problems, your exam problems for exam 3, which is a week from Tuesday, you'll just submit this problem maybe you did over the weekend or something, because I only really want you doing it one time. So I do think it's important to know the relationship between a graph and where the first derivative is zero, or understand that when the second derivative is negative, it's concave down, because the one thing about a calculator is that the output's only as good as the input. And I have seen students um, not deliberately misuse your calculators, but they make an error, and then they look at the answer and they just a lot of sometimes we just automatically accept whatever comes out of the calculator. And I can't remember once a student graphing something like x squared plus one, a parabola that was clearly above the x-axis, and his graph was below because somewhere he made a mistake. So you'll go through this one exercise of how to create a graph using all this information, and that's the only time we'll do it in the course. So I'm going to show you a couple of examples here, one that are in these notes and one that I did from my lab. Okay, so some of the information we're going to use is, first of all, definitely the asymptotes. When you create a graph, you have to know what the asymptotes are. We want to know the domain. I guess I should look down here. So yeah, so definitely the domain. So it's a square root function, or a place where the denominator is zero, that's not in the domain. Then we have to take into account the asymptotes, both vertical and horizontal. Knowing the intercepts can help. It's definitely easier to find the where the curve intersects with the y-axis, just set x equal to zero. So x-intercepted can be kind of hard sometimes. And then let's use the first and second derivative to find where the curve is increasing or decreasing, or just to analyze the concavity. Okay, so let's just look at this one. There's lots of examples in here, so we're only going to look at one. And I do think this is a little bit on the, because I'm not, the easiest is definitely a polynomial, but it's not necessarily the most exciting thing in the world. But I think definitely if we can go through this exercise, it really demonstrates that we've learned a lot. But yeah, it's really only meant to be done maybe one or two times, not over and over and over again. And let me see if I can find the problem that I wanted. There's a very exciting problem. Yes, example 6. We're going to do example 6, and then the problem 12 from the homework. So let's say we wanted to graph 4x over the square root of x minus 3. Now, of course, what we would normally do is just take our calculator out. I like going to, when I have my computer with me, there's the website, Wolfram Alpha, and they give really some very nice graphs in there. So, but of course, in your classroom, you can't have that. I guess if you have your phone, you could. Okay, so let's just look at the domain. Well, clearly, because of the denominator, it's a square root. We want the square root to be positive, so it's x greater than 3. And then we have this vertical asymptote. So as x approaches 3, the denominator goes to 0, and so it'll go to positive, right? Go to positive infinity as x goes to 3, because the numerator is positive, and the denominator will go to 0. Now, what about we're kind of abbreviating here, HA, horizontal asymptote. And so now we're looking at for super large x, like x almost at a billion, a trillion times a trillion, or a trillion times a trillion times a trillion. And even though we're not close to infinity. Okay, so So for large x, that kind of looks like the function 4x over the square root of x. So that goes to infinity. So there's actually no horizontal asymptote, but what you can see for large x, it kind of looks like the square root function. So we're going to see that later on. On the intercepts, you just let x, well, if x is 0, y is 0, but x equals 0 is not in the domain, right? X has to be greater than 3. So there are no intercepts. And so, and if you set y equal to 0 and solve for x, once again, then x would be 0, except x is not in the domain. Okay, so there are no intercepts for this problem. Okay, so first derivative. Okay, so we just use our friend, the quotient rule, and then we go through all these steps. And eventually, if you simplify it, yeah, so here are the steps right here. I'm pointing my arrows at it. So hopefully we're really very good at this right now. So when we take the derivative of 4x over the square root of x minus 3, we end up with 2 times x minus 6 divided by x minus 3 to the 3 halves. So clearly that's 0. The first derivative is 0 at x equal to 6. Okay, so now that 6 will then divide the domain up into these two open intervals from 3 to 6, and then from 6 to infinity. And we just choose one point in each and evaluate the derivative function. So like when x is 4, like 4 minus 6 is negative. So and then the denominator would be positive. So it's decreasing from 3 to 6. And let's take a number greater than 6, like 10. And then the value of the derivative is positive. So we know that the derivative is positive for x greater than 6. So from 3 to 6, the function is decreasing. And from 6 and above, 6 and greater, the function is increasing. Okay, so now, yes, it is second derivative. So second derivatives aren't always that fun to take. Like, I mean, if it's a polynomial, then it's fine. But yeah, you get the first derivative, it's a little messy. Oh, now the second derivative is even messier. So again, we're using our really very good friend, the quotient was so good I forgot the name. Okay, so so we're going to use our friend the quotient rule to take the derivative, to get the second derivative, the derivative of the derivative. Okay, you can see here, it's x minus 3 to the 3 halves. Derivative of the numerator is 2, and then 2x minus 6 times the derivative of the denominator all over x minus 3 to the 3 halves squared. And students, I'm going to let you get to this step and this step. I'm going to let you do the algebra. And what we do, if you simplify it enough, the numerator is going to be minus x plus 12. And it's going to be divided by x minus 3 raised to the 5 halves power. And so you get a point of inflection at x equal to 12. Okay, so now 12 divides the domain up into these two open intervals from 3 to 12. And then from 12 to infinity. So again, once again, we can just take one point in the interval here. And so yeah, so let's say it doesn't actually have the numbers here, but let's say if you take 9 from 3 to 12, yeah. So negative 9 plus 12 is positive. And yeah, 9 minus 3 to the 5 halves is positive. So okay, so it's going to be positive. So just by taking 1 point from 3 to 12, in this case, x equals 9. Yeah, we see that the second derivative is positive from 3 to 12. And then if we take, let's say, like negative 15, right? Okay, x greater than 12, we just try 15. Well, negative 15 plus 12 is negative. But yeah, then again, 15 minus 3 is positive. So for x greater than 12, the second derivative is negative. So it's concave up from 3 to 12, in the open interval 3 to 12, and then concave down. Here's this, a little hard to tell in this graph, but you can kind of tell that it goes from an upward facing U to a downward facing U. If we kind of did, and the other thing, students, is that for very large x, is what we were saying before. There's no horizontal asymptote, but it kind of it approaches something like the square root of x, and this, so it kind of looks like the square root of x a little bit. The square root of x is definitely a concave down function. And yeah, the only thing I might have included in here is just the value. I would just label the points of the I do that in my next example. I would label the points of the at least of the critical points. Okay, but yeah, but you definitely have this point of inflection right there where it goes from concave up to concave down. Okay, so let's just do one more. Now you can see here that no one's going to have the patience to do this over and over and over again. Now, my lab, they have a bunch of problems using this graphing technique. So if you want to, you can, but it's all, in the end, you're not typing that into my lab. So it's, I guess it's the honor system. Okay, so now here I took one of my favorite problems on my lab. Okay, and it's number something or other, 12. Okay, x squared plus 15 divided by the 4x plus 1. Yeah, so there, see, this is what I'm saying. It says use the guidelines to make a complete graph of f. So, my guess is a lot of students would just use the calculator, get the answer. And if I was a student, I'll be honest, I might do the same thing. So graph the function using the, because you really only need to do this once, or you really only need to do it once and to turn it into me for exam 3. Graph the function using the following information: the domain, the asymptotes, the intercepts, the first derivative. I labeled second derivative twice as 4. It should be 5. Okay, so find the points of inflection where the graph is concave up or down. And okay, so the domain is all real numbers, of course, except for x equals, you solve 4x plus 1 is 0, and you get x equals negative 1/4. So x equals negative 1/4 is not in the domain. So there's actually an asymptote at that point. So as we go to negative 1/4 from the left, the second coordinate goes to negative infinity, right? And as we go from negative 1/4 from the right, y goes to a positive infinity. Okay, so because the numerator is always positive, so 4x plus 1 is less than 0 for x less than, right? So we know that the vertical asymptote goes to negative infinity as we approach from the left, and we know that 4x plus 1 as we approach from the right. 4x plus 1 is always positive when x is to the right. Okay, so we know, so as far as the vertical asymptotes are concerned, it occurs at x equal negative 1/4, and as we approach from the left, it goes to negative infinity, and as we approach from the right, it goes to positive infinity. Now, here's something we didn't. Okay, so that's what we get as far as vertical asymptotes. We did this next step like horizontal, or what happens when x goes to plus or minus infinity. I don't think we really did this a lot in that unit in asymptotes. I can't remember the unit number. Okay, but what I did was I divided, so the function is x squared plus 15 over 4x plus 1. So I divided, it's actually going to behave like a line, a slant, not a horizontal line, but a line with some slope. So for x plus 1, we get divided into x squared plus 15. It turns out, yes, I'm going to do the long division. 4x goes into x squared 1/4 x times. And that x, looks like it's in the denominator, but it's really in the numerator. Okay, so and we just do a little bit of algebra, something we learned in our algebra courses probably a very long time ago. And so we multiply 4x plus 1 times 1/4 x, so we get 4x squared plus 1/4 x, and so we subtract, so we get negative 1/4 x plus 15, and then 4x goes into negative 1/4, 1/16 times. And so what we get here is that x squared plus 15 over 4x plus 1 is 1/4 x minus 16, minus 1/16. So the x squared plus 15 over 4x plus 1 is 1/4 x minus 16. So it looks like that straight line with the slope 1/4. And then it has this remainder, 241 over 16 times the quantity 4x plus 1. So I'm saying, so for a very large x, we know that this term, this part that I'm circling right here, we know that that goes to 0. So for very large x, this function, where you have an x squared in the numerator, and that's the largest degree in the numerator, and the degree in the denominator is 1. We know it behaves like a straight line, or it's going towards a straight line for x, going up as x gets closer, plus or minus infinity. Again, we didn't really talk about that too much. So if you didn't put that in your answer, that's in case we have a problem like this. It's not the most critical thing. Okay, intercepts. Okay, so the function is x squared plus 15 over 4x plus 1. So yeah, so you let x equal 0, your y is going to be 15. And yeah, so and there are no solutions to you let y equal 0. Well, x squared plus 15 is never 0. So there's no y-intercept. So now we're going to take the first derivative. And so yes, we do a little bit of work here. And we end up with, yes, we use again our friend, the quote. I keep saying the quotient rule is my friend, but okay, so okay, so yeah, so it's so we just use so it's the derivative of x squared plus 15 2x times 4x minus 1 minus x squared plus 15 times 4 all over 4x plus 1 squared, and we do a little bit of algebra here, and we get 4x squared plus 2x minus 60. And when is that? When is the numerator 0? So we can just use the what is it, the quadratic formula, and we get about, I do a little simplification. And so we know that the critical points occur at, just a little bit to the right and the left of the vertical asymptote, x equal to -1/4. So it's -1/4 plus square root of 241 over 4, -1 plus or minus the square root of 241 over 4. Okay, so it's, I don't know, it's about, I don't know, like 3 or something. I don't know. One plus, yeah, it looks like it's maybe 241 is maybe something like 12 divided by 4. You get like 3, and you multiply by square root of 2. Okay, well, anyway. Um, okay, so yeah, so anyway, so we get the vertical, yes, so when we consider the intercepts, remember the function's not continuous across the intercept. So we break this the domain down into intervals. We have to use the intercept -1/4 as one of the delimiter points. Okay, so we want to know where, as far as increasing or decreasing, we want to know, okay, so we have the interval from -infinity to the smaller critical point, -1 to minus 241 over 4. Then the second interval is the smaller critical point, -1 minus 241 over 4 to the intercept, -1/4, the vertical intercept. And then -1/4, the third, this one right here, -1/4 to the larger of the two critical points. Oh, and I guess I should have a -1 here. And then the second, the larger critical point to infinity. And okay, so now let's look at the value of the derivative in these four intervals. So it's going to be all positive or all negative, because you have to pick a point. But let's say you take values of x near infinity. So the derivative is 4x squared plus 2x minus 60. Well, the denominator is always positive. And for very large values of x, and you pick x big enough, eventually 4x squared plus 2x minus 60 is positive. So we know that the derivative is, so for these end derivatives here, I mean, those end intervals, -infinity to -1 minus 241 over 4, and -1 plus 241 over 4 to infinity. We know that the derivative is positive, and so the function is increasing in those intervals. Okay, let's say we're approaching -1/4 from the right or the left. Yeah, the derivative function is going to be negative. And here's the derivative function. Yeah, so when x is really small, well, x is like about 1/4, that minus 60 is going to dominate, right? So if you pick so I'm looking at these, considering these two intervals right here. The one I'm putting, maybe I can just. So I'm considering these two intervals right here. So I know the outer intervals, the first and the fourth one, the derivative is positive again. So if you get near x near 1/4, this minus 60 term here is going to dominate. So when x is near -1/4, the derivative is negative. Okay, so the derivative is negative everywhere in the second and third interval. So it's plus. So increasing, decreasing, and then decreasing and increasing, which might seem strange, except there's a discontinuity. We actually have to take our pencil off the paper to graph. Okay, so, okay, so, okay, so now let's look at, so we know where the function's increasing or decreasing, and now you have to go through the painful step of taking the second derivative. Okay, so again, we just use the quotient rule, so remember, here's the first derivative, it's somewhere. Oh yeah, it's somewhere, yeah. 4x squared plus 2x minus 60, 4x squared plus 2x minus 60, and we just take the second derivative of that, and yeah, we get, yeah, so here's the second derivative right here, and you just do some algebra, and I'm pretty sure I checked this. Oh, it kind of comes out nice, though. The second derivative is 482 over the expression 4x plus 1 cubed, which means that it's always positive. Remember that x equals 1/4 is x equals negative 1/4 is an asymptote. Okay, so so in this case, it's always the second derivative is positive to the right of the asymptote, or for x greater than 1/4, and the second derivative is negative for x less than negative 1/4. So the curve is concave up for when you're to the right of the line x equal 1/4, and it's concave down to the left of the line x equal 1/4. So now we're going to graph. So I just have this kind of crude graph here, but it does kind of conform here. So here is the point of, here's the critical point right here. Okay, so so you get this minimum right here. Yeah, again, you can use a second derivative, right? It's concave up. You have a critical point, so you know that it's a minimum. So you know that negative 1/4 plus 241/4 represents a minimum, and you know that the other critical point, well, it's concave down, so you know that represents a maximum. And so when you plug in the smaller of the two critical points, you get negative, I'm having a little hard time reading this, -4. I think it's -4. 0.31. Okay, and then again, so again, it goes down to infinity as we come from the left, as you go to 1/4, and as you go to the right from negative 1/4, it's positive infinity. And one thing I did not label here was the intercept 0, 15. So students, it's kind of, graphing by hand is not easy. Oh, another thing too is that you can see that is for large x, positive or minus, yeah, it's approaching this line, negative 1/4 x minus 16. So that's all there is to it, students. And then, so you'll do something like this. So I don't expect your drawings by hand to be beautiful. So I'm just going to stop right now. This, let's see here. Stop the